So yes, thank you for letting me share with you some of my ongoing thoughts about changes in life expectancy, especially during time where mortality changes pretty rapidly, and how we try to give some meaning to those numbers. So I cannot. No, okay. Sorry, I'm back. So the context of this is that change in period life expectancies are one of several potential measures for mortality shocks. Josh and Ron had a paper in the Proceeding of the National Academies of Science gives a number of indicators for the impact of COVID mortality, for example, in the US. In my reading of the literature in the past couple of years, my impression is that life expectancy at birth and changes thereof is the indicator that's favored by many demographers. And there's several reasons for that. I think the one we can all agree on is that it's independent of the age structure. So it's, in that sense, it's a pure measure of mortality change that is not affected by age structure that may vary across population, for example. It's also, I think, a measure that is more, it has a unit, sorry, that is probably more appealing than other measures you can think of that do not take into account age structure. So you could measure, for example, age standardized death rate. Then you would have a change that is something in deaths per person years, and that's not really easy to get an intuition on, as opposed to life expectancy and change in life expectancy that are expressed, it's in inverse of basically a death rate. So it's years per person, which has some kind of intuition to it, although I'm going to argue that the intuition can be misleading here. And then the third point is that it's comparable. I mean, we have time series of life expectancy at birth for all countries in the world since 1950, thanks to the UN, and in a number of countries going much beyond that. So we can compare the drop in life expectancy that has been induced by COVID, for example, to what has happened with HIV AIDS pandemic, or going further back to the Spanish flu pandemic. So for all these reasons, the life expectancy change seems to be attractive. But if life expectancy at birth itself has a nice interpretation, changes in life expectancy, I'm going to argue, are more tricky, because the intuition we get from a number that is a life expectancy at birth, I think every grad student get that in their first demography course, is that kind of thought experiment where you have a cohort of people that live their entire life through fixed mortality conditions, and the average age at death, so how long an average person can expect to live is provided by life expectancy at birth. But this is based on this thought experiment that mortality would not change. So my question here is, like, can we have some intuition for what it means when life expectancy, when mortality conditions do change, to what is the meaning of that number, the difference in life expectancy at birth? So let's go back to the drawing board for a second. So the main interpretation, life expectancy, of course, is a life table indicator. The main interpretation of the main framework for understanding life table, the period life table, is to think of it as a synthetic cohort. So in a real cohort here, you have a cohort members. It's a close, let's say close cohort. Everybody died at some point. So once every members of the cohort has died, we can calculate the life expectancy, which is basically the average age at death of the cohort member, by looking at how many years has each one lived, which is basically the age at death, and how many have died at different ages. So it's a weighted average here of, it's a sum of the age times the number of people dying at that age, divided by the total size of the population. Since everyone dies, if you sum across all the deaths, you have the total number, the initial size of the birth cohort. So in a pure life table, basically what we're doing is we try to mimic what a real cohort is by assuming that we have these people who come at some certain point are going to be subjected throughout their lifetime to the same mortality condition. So life expectancy at birth in a pure life table is basically the same thing with the decrement of the life table, the little d's. which are basically the product of the number of survivors times the mortality rates for at that age for the survivors, right? So basically, it's an average age at death, and we're trying to reproduce that image. If we move to the difference in period life expectancy at birth between two populations, let's say, or between the same population at two different times, the expression for that was derived by Pollard, and I write it here. So I'm using 1 and 2 for this a subscript for the two, either the two population or the two period for the same population. I don't know how. I couldn't see really the setup for your room, so I don't know if that's easy to read. To add some visibility to it, I've highlighted in red everything that refers to the second period. So basically, we can rewrite this a little bit. What I did here is I go back to a positive difference between the mortality rates at time 2 and time 1. This is why I have a minus in front of the ratio, and I've expanded this probability of surviving from age 0 to age A as a ratio of the L number of survivors at age A divided by number of survivors at age 0, which again can be thought of as a sum of all the decrements. So the full extinction of the chord, synthetic chord that is representative of the life table means that L0 is basically the sum of the deaths across all ages. So
Patrick, just a notation question.
Yeah.
AP0 is the chance of surviving to age A?
So it's a probability to survive from age 0 to age A, yes.
Up to age A. And the difference between that and LA is not necessarily normalized. It could have any radix. Yeah,
I did. I mean, if you take a radix of 1, then they're the same. But I haven't made that assumption yet.
No, just wanted to clarify. Thank you.
Oh yeah. So this is why I have this denominator here. And so basically, we see that we can make kind of sense of that difference if you think of, let's say, a change in mortality condition. Here, what you have is the difference between the mortality rates, so how much the mortality rate have increased. And when you multiply by the survivor at that age, what that gives you is a number of additional deaths at that age that comes from the mortality increase. And when you multiply by the life expectancy, these people who died due to the increase in mortality, that's the life expectancy they would have had in the previous condition. So this is an expression of how much years of life were lost due to the increase in mortality. And so there's some situation, I'm going to argue that some situation where that makes sense. I mean, using this framework makes sense if we're comparing two populations and we assume that mortality don't change. So we could say, in a stable regime, this is how much a child who was born in Sweden, how much longer he's going to live compared to if he was born in the United States, for example. There's another classic example of that where drawing from Kifitz, who said, what would happen if we were able to eliminate all cancer mortality right away? So basically, you have two hypothetical scenarios here. One is, mortality will never change, will remain what it is. And the other one is we instantly eliminate all cancer deaths, but everything else remains the same. And we're comparing those two, basically, to these two steady states, and we can actually derive some intuition in that way in life expectancy, how much one would live without cancer on average compared to how long someone lives now. I was told to do shorter rather than longer. So this is kind of a little bit tangential to my arguments. I can skip that. Basically, this is, again, from Kifitz, when he started to illustrate what the effect of eliminating a cause of death, he started to derive equation based on this proportional mortality change. So assuming that what happens is at every age, the mortality rates change by a fixed fraction of what it was before the change. And if you derive this equation, if you plug that into Pollard's equation, you get this equation, which is very familiar, should look pretty familiar because it's pretty close to the equation that, I don't know, maybe something you've seen during the workshop. Goldman and Lord have shown that the entropy factor that Kifitz has put forth can be written this way, which is pretty much the same very similar to this equation, except that this one has life expectancy at time 2, as opposed to life expectancy at time 1. But if you do Taylor expansion, you can show this is the same thing. So you basically derive that equation as well, which is a nice way of summarizing this. And you can even introduce here, Josh referred to Jim Vopel, so I thought I could maybe give a nod to Jim and the paper with Vladimir on e-dagger. But since this is not quite central to my argument, I'm going to skip that, and I'm happy to return to that in the Q&A if somebody is interested. So basically, to recap what I've been arguing here is that this is we can think of this difference in period life expectancy at birth in this synthetic cohort framework under for some type of mortality changes. Either we compare actually two populations that have time invariant mortality regimes, or we have two hypothetical permanent changes, or sorry, a permanent regime and a hypothetical permanent change in that regime. So that's a classic example I was referring to. But this is really problematic for temporary mortality changes, what I call shock. So if you can assume that this difference here is going to last the lifetime of an individual, then the metrics you get by through that difference in life expectancy, I'm arguing, is not that meaningful. So what am I suggesting to do instead? Well, there's a second interpretation to the period life table, and you probably know that if you've been using the right textbook. It's to see it as a description of the stationary population. So it's a stationary population that has the same mortality rates as the population in interest. But it is stationary, that is, you condition the number of births, the fertility regime, so that the number of births remains constant. And then if that's the case, well, then if you compare, this is life expectancy at birth. This is the equation I've shown you before. And this is in the real population, this is the mean age at death. So in the real population, you have the number of deaths, which is a product of the same mortality rates, but applied to the actual number of people age A. And so this is the difference between the two. So if you think of this stationary population model or framework for looking at a life table, what we have here is something like a standardized, when we go from the mean age at death to life expectancy at birth, sorry, we get something like a age standardized mean age at death. But it's not an age standardized in the classic example where you get an external standard, like for example, the US Bureau of the Census provide a standard population, I think every year, and you could use that to standardize death rate across different states. So the difference is not affected by the differences in age structure. So that's a classic example. Here I'm going to refer to what we're doing here as an internal age standardization as opposed to the external one. That is, we're looking at the stationary equivalent of that quantity. That is, what would be that quantity, what would be the mean age at death if the population had the same mortality rate but was stationary instead. So we substitute basically the age distribution with the survivor curve, basically the distribution of surviving members of a birth cohort. So I'm going to call that an internal age standardization. I don't think there's a term for that. I think I just made that up, but I'm going to stick to it. So if you want to compare across two populations, you could object that this is not really a real standardization. It's problematic because then you compare two populations. You standardize them with different, you're not really standardizing them. You substitute different age distribution if they have different mortality regime. But nobody's perfect, and I'm going to argue that external age standardization has actually some issue as well. For example, if you go back to the thought experiment I referred to, the sort of the classic example of mortality rate changing by a fixed fraction. So if each mortality rates decline by 10%, basically the mean age at death, once you age standardize the mean age at death, it doesn't change, right? So that's not really a nice property, because the intuition is that if mortality declines, then the mean age at death should increase. We should kind of live longer. And that intuition is not entirely wrong, because it sort of works through the changes to the age distribution that the mortality decline would induce. Mortality decline should in general imply an older age distribution. There's some exceptions. You might have seen in your encountered what we call a neutral mortality decline, where the mortality rates change by the same number, so not by the same fraction, but the same absolute number. But in general, it does. So the problem that I'm seeing here with using external age standardization is that it removes changes in the age structure, but it also removes those that are induced by the phenomenon of interest, which is that mortality is declining. So the internal age standardization that I'm using here, or I'm suggesting to use, allows the age distribution to change, but only as a result of mortality change. So the only thing that's going to change if you do compare two populations with their internal standard is that the survival curve is going to change. So maybe not appropriate to compare to population, but I think fairly appropriate if you're looking at the same population at two different points in time, and the internal standard would be different because mortality changed. And I think, to me, that seems to be perfectly fine to do that. Actually, probably better. So if we do that, if we accept this framework of using the standard, an internal standard, or using the stationary equivalent age distribution, what's happening is here we have the, am I doing on time? I think I still have 5 minutes or so. So this is the equation I've shown you before, and the stationary equivalent of that would be, again, substituting the actual age distribution of the population instead of the survival curve. So basically, the difference in life expectancy at birth, which is this, is the stationary or internally standardized equivalent of that thing. And to restrict my argument here to mortality shocks, which was my initial interest, what you have in the denominator here, the product of the difference in rate, let's say an increase in mortality rate, multiplied by the number of people at that age now at the second time, that's that's called excess deaths. That's excess mortality, that deaths that occurred at time 2 that wouldn't have occurred at time 1 if mortality rates hadn't changed. So I define this quantity here that I came up with that term. I don't know if it's the right description, but I call it the mean unfulfilled lifespan. The unfulfilled lifespan is basically the product of excess deaths at a certain age, multiplied by the life expectancy at that age in the previous condition. So this is how many more people have died because of surge in mortality, and that's how long they would have died in the initial mortality condition. So the sum here is all the the years of life lost, and divided by all the deaths, providing a mean for the entire population. And so basically, the difference in life expectancy, the minus sign here has disappeared. So the difference in life expectancy at birth is the standardized stationary equivalent of minus this mean unfulfilled lifespan. So basically, what I'm arguing is that it's better to think of of life expectancy at birth not so much as a forward-looking and a kind of a prediction, an expectancy of what's going to happen, but more looking back at people who actually died during the recent period, during the mortality surge, and treat it as a measure of premature mortality. So in the few minutes I have left, I just want to introduce a few other concepts of, a few other measures of premature mortality that you might have seen and compare it to the new indicator that I'm proposing here with the MUL. The main one is the years of life lost, right? So this is a number, this is very close. You have the number of deaths from a cause, and then there's two approaches to measuring years of life lost. One uses a life expectancy from a standard or universal life table, typically meant to represent the maximum longevity. So it's usually from a low mortality country. And if you do that, this has some advantages, because if you have, basically you have additive properties across population. So you can derive global estimates. If you calculate this quantity for all countries in the world, for a given cause, you can calculate global estimates of years of life lost to certain cancers and so on. This is basically what the global burden of disease does. But it's not really realistic if you think of a practical example. For example, if you want to know how many years have been lost to COVID in the US, it's much better to use a population specific here, the US life expectancy, life tables and life expectancy values. So, so the MUL is is related to that quantity, right? So if you think of basically the years of life lost to excess mortality, to the mortality surge, you have basically this equation at the top. If you use the life expectancy values that were before the mortality shock. So the relation to the MUL is pretty standard. The mean unfulfilled lifespan is just the the years of life lost to excess mortality divided by all deaths. So it's an average.
So, Patrick, so what D superscript 2 is not the number of deaths squared. It's, what is it?
No. It's sorry. Yes, it's a confusion. That's why I use red color to.
Yeah. So just say it in words. What it is?
It's a number of deaths in the second time period. So I'm comparing two time period. One sort of before, let's say before COVID 2019, and after COVID 2021, let's say, or during the mortality surge 2020 2021.
Okay, so if I divide, if instead of in the numerator, instead of having D2, if I had the number of deaths from the cause, or the number of excess deaths, the total, then it would be the average person years lost per excess death, right?
Yeah. So I'm getting to that.
Oh, okay.
So maybe let me show this, and if it doesn't answer your question, remind me at the end. So yes, so the years of life loss is depends on population size, right? So it doesn't have a denominator, so it makes it difficult to compare across population. The US is a bigger country than Germany. Of course, it's going to have a higher number of years of life loss. So to standardize, people use a denominator and use this term average years of life loss, but there's not a standard understanding, at least what I saw in the literature, about what is the right denominator. So some people do years of life loss to a cause divided by years of life loss to all causes. Some people do years of life loss to a cause divided by deaths from all causes, which is what I've done with the MUL. Some other people are doing what Josh was just suggesting, taking years of life loss to a cause divided by the deaths from that particular cause. And so this is what I'm actually using here, what I call the population specific, to emphasize the fact that I'm using life expectancy value from that population, not a universal quantity. And I divide the numerator by the number of deaths that are excess deaths. So I think that's what you were referring to. And if you do that, then the mean unfulfilled lifespan is the ratio of excess deaths, the proportion of all the deaths at time 2 that are excess deaths, multiplied by this average, which is an average number of years lost by from excess deaths. So if you think, let's say, to simplify, if you think that all excess deaths is COVID deaths in the past 2 years, that would be how many years on average someone who dies from COVID could have expected to live if they hadn't died of COVID. I have one more thing, and I think I'm out of time probably. Another useful indicator of excess mortality is called the P score. It's basically the proportion of deaths that are excess deaths relative to what we would have under expected condition before the surge. And so you can, I don't need to go into the detail, you can play with the number 2 there, and you get that equation at the bottom. But basically, the mean unfulfilled lifespan is that ratio of involving the P score multiplied by the average that we just discussed. So my very final slide is to summarize that I think interpreting the difference in life expectancy at birth in that framework of a synthetic cohort that is looking forward is problematic for mortality shocks. I don't think the difference in life expectancy at birth tell us anything about the life expectancy of people, or how mortality or life expectancy has changed for people who are still alive in the US today, for example. I prefer to use what I call a backward-looking framework that is more about premature mortality for people who did die during the recent period. And I think that's where the difference in life expectancy is more meaningful. And actually, the difference, the opposite of that difference is actually what I baptized the mean unfulfilled lifespan, which can be interpreted as the mean, that is mean per actual death. And again, going back to Josh's question, all death. So the mean reduction in longevity due to the increase in mortality in a recent death cohort. So it's not a property of a synthetic birth cohort, it's a property of a recent death cohort, basically this total D at time 2. And the value of that indicator depends on this average years of life lost per excess deaths, which I just discussed, and on the P score, which is basically the prevalence, sorry, the incidence of excess deaths among all deaths, and that's it. So I have a version of the paper, full version of the paper online, but it's not, I haven't really updated it recently. So that's it. So let me stop. Right.
Thank you, Patrick.